probably the transformer. Yes, sir.
You still haven't answered my question.
I didn't hear you.
Okay, a monopolar, one-axis magnetic field
Sure.
of 20 Gauss
Yes.
per square centimeters.
Yes.
Can you describe that field? Can you describe it in force, pounds per square inch?
Well, you're getting off into
anything.
Webers and a whole slew of other things, and I'm afraid we'll lose the audience when we start doing that.
Well, would you describe this 20 Gauss force of 1
20
square
Gauss
centimeter as tremendous, minimal?
To someone who tremendous depends on what the individual is looking for.
Okay, lifting 50,000 pounds and accelerating it to approximately 30,000 miles an hour in about 5 seconds.
Okay.
Would that describe it?
That is getting in the area, I do believe.
Okay, that's all I want to know.
I'm at the age where my mind doesn't go around corners real fast, so if you get to me after the meeting, I can answer you, but
I'm sorry, I didn't mean
to get off the track.
I didn't mean to prick your brain.
No, I can answer you in great detail, but I'm not sure that I would lose the audience in the process.
But 20 Gauss is a large amount of magnetic.
20 Gauss based on a human being, and what a human being can tolerate is 20 times 100 milligauss now. A Gauss is 100,000 volts magnetic flux equivalent. So you can transfer that into horsepower by dividing it by 746. And then once you get the horsepower, then you can relate to what the fellow was asking back there. It's a lot of horsepower. A lot of horsepower. 100 magnetic flux equivalent based on Gauss's original definition, which does not correspond to what the university textbooks have in them, and most of the electrical books, when they describe a Gauss, the person that wrote the book is not aware of what Gauss's original definition was. But the original definition of a Gauss was the magnetic equivalent of 100,000 volts RMS. Yes,
we're recording now.
Two-part question real quick.
Okay.
First part is, will your power circuits operate without an earth ground? And second question, is your power circuits operate near the vicinity of any radio towers or power lines?
Actually, if you're in the vicinity of a radio tower or anything that puts out a lot of electricity like a power line, you don't need anything else. You can build you a coil and tune it to the frequency of whatever it is that's putting out the large electrical flux, and you've got a free ride. And you're not stealing from them. The power company will come out and haul you off to jail and claim that you're stealing their electricity. That's not true. Basically what they're doing, they're throwing away all of this energy that's bleeding off in the form of magnetic energy from, say, a power line or a machine or whatever is wasted energy. So that's how they assure that you always get back less than you put in. But the amount that's being lost is equal to the amount that's there.
Sure, we agree. I was wondering,
so if you got 50%,
near one then? Do your power circuits have to be operated near a power line?
No.
Okay.
No, but if you want to, you can tune it into the radiation belts and run off of the radiation belts, and you don't need any other thing if you know what frequency the radiation belts are.
So I take it that you do need an earth ground for your circuits?
You need what?
You do need an earth ground.
When you speak of ground, there's air ground and earth ground.
Right.
And the antenna, say, of a radio is grounded into the air, and then the earth ground is the other part of it.
I'm talking about an earth ground, in the ground.
Do you need an earth ground? Probably, if you're anywhere near metal objects or not too far off the ground, it will ground itself. And it will, especially if you stick your hand on it and you're standing in a bucket of water.
Well, that is an earth ground.
Okay, are we about ready?
Yeah, we're ready.
Okay, well, what we're going to do is kind of start at the front end and work backwards and see what comes out. And I'm going to look at my notes here a little bit so that I don't get off the track. But the importance of what we're doing here relates to the human condition and its most complex manner. And in order for human beings to survive, the oxygen level has to be a certain amount, and that critical amount starts kicking in at about 15%. And the best case worldwide today is either 15% or slightly more. If you're in an area where there are a lot of trees and vegetation and other things, it may be 17 or 18%. But if you're in a large city like Mexico City, Tokyo, Jakarta, Indonesia, and any number of other cities like that that have populations greater than 20 million, the oxygen level there is 7%. And what happens when it gets down at that level, all of your disease mechanisms, your viruses, all of them, none accepted, all of your germs and other disease-causing things are anaerobic, which means that they thrive in an absence of oxygen. And with this in mind, if you go to Mexico City or Tokyo or someplace like that, they have these little machines around in the buildings and on the street where you can drop your nickel in and get some oxygen or ozone. And it's that bad. So one day, very soon, unless this thing is reversed, you're going to have hundreds of thousands of people dying a day in all these large cities. And they'll die from every complication imaginable because their immune system quits working whenever the oxygen level goes down. And at that point, if you don't have adequate oxygen in your system, your immune system can't do its job. So even the simplest thing like a bad cold can kill you in a matter of hours. So what can we do about this? It happens that 1 gallon of gasoline, when combusted, uses or chemically combines 200 pounds of oxygen from the air in such a way that it's no longer available for the creatures that need it. And it's out of the system basically forever unless the trees or vegetation or something can put it back into the system. And we have fewer trees and less vegetation every day, and it's not keeping up with the amount of oxygen that's being taken out. Now that may not sound like all that much, but there are 4 million barrels of gasoline used every day, and there's 44 gallons. And if you have your pencil, you follow me here, 44 gallons in each barrel. So it's 4 million times 44 times 200 pounds of oxygen, and you'll see how much oxygen each day is being taken out of the system more or less permanently. And this has been going on for quite a while. We know this because back in biblical times, they have a piece of rosin that had about 39% oxygen ratio to nitrogen. So the air you breathe is mostly nitrogen with oxygen in it. So we come along to about year 2000, and year 1900, and we have at that point roughly, let's see, I have a chart here on it. At that point, we have somewhat less than 30% ratio. So we dropped from about 40 down to 30% from biblical times to 1900. Okay, Carl Sagan in 1984 in his book Blue Planet listed the oxygen ratio as 18%. The federal government publishes statistics on this, and the present level is about 18% or less. It's more likely 15%. You can put this on a chart, a decline chart versus years. You have your years, and you have the percent oxygen here, and it breaks a straight line, and sometime just shortly after year 2000, you won't have any more problems. No, everybody's problems will be solved sometime shortly after year 2000, unless we get the balance back in our favor. Now, there's only one way that I'm aware of that can happen. All of the energy producing methods that are available today have problems. For example, in wind energy, wind power, the wind has to blow constantly and dependably in order to have a large, massive amount of energy. And you're at the fate of nature, which is rather fickle. So you can depend on some energy, but you can't, for large, massive amounts of energy, you're in big trouble. Wind power will work on certain conditions, but it does not work well if there are massive amounts required. Now, atomic energy is something which takes you back to the age of the steam engine. It may sound exotic and a lot of other things, but basically what happens in the atoms coming apart there, you generate a certain amount of heat, and that heat makes steam, and that steam drives steam engines. And when you're when the stuff has to be transferred out, you have a big problem of how to get rid of it and the disposal on it, and you have a lot of other potential disasters looking you in the face. So atomic energy, the reason why it's popular is because it uses massive amounts of tax dollars, your dollars, and fed through the bureaucracy. That's a source of enrichment. So the fact that it's not really all that favorable is more political than anything else. It's not your interest that's involved, nor your money. Are you getting your money's worth out of it? So with that in mind, you'll notice that 100 years of the, this is the chart I was talking about, and in 100 years you can see the amount of oxygen at the present rate, daily use of consumption, that it's never going to make it to 100 years. It's never going to make it even 10 years from now. So, that's very obvious whenever you look at the statistics that are there. I assume the government is aware of it, and a lot of other people are aware of it, but they're not. It's not convenient for them and their way of doing business to say anything about it. They kind of hope it will go away, I suppose, but it's not very likely. So the only source of energy that is non-destructive, that's universally available, that's free for the taking, just like a fish, if you go out when you catch a fish or that sort of thing, would be the energy from electrons. And the nice thing about electrons is that when you flip them, there's a magnetic side and there's an electrical side to it, and they're both equal. That's your equal and opposite that everyone will tell you that you've always got an opposing force to whatever. So when you're flipping electrons, you flip it, say one time, you get a unit of magnetic energy, and then you flip it again, you get a unit, as it flips back to its normal position, you get a unit of electrical energy. So the speed that you flip these things at depends on how much energy you get out. It's just like an electric motor. Whenever you have the magnets and the coils spinning past each other, what's happening there, the electrons in the vicinity of where you are being disturbed, and when you disturb them or pulse them, they do their flipping thing, and when they do the flipping thing, you can harvest the energy that you're wanting, which would be electrical in this case. So the speed at which this generator goes, if you run it, say, at a certain number of RPM, like say 400 RPM or 2,000 or whatever, and if you double that, you will get a considerable amount more electricity. It's not a straight curve. As you start disturbing electrons up to about 600,000, let's see, I believe it's 600,000 cycles per second, at that time you're into the speed of light. Below that, you're well below the speed of light. And that brings up another question, because they have any number of authorities around the world, and not a one of them came up with the same figure for the speed of light, and it varies considerably between the authorities. So if you read a book and it tells you the speed of light is so-and-so, they are accepting someone's numbers, which are probably open to question, because the different people that come up with these different numbers don't like each other. And they hold a conference, a worldwide international conference, and they all got together and they agreed on one number which would sort of take care of it. It's kind of in the middle. So the speed of light is not a certain thing at all. We can go from that to some of the devices that of interest. There are about 6 or more devices which I'm directly involved in. And if you'll pardon me, I think we'll go back to this question of free energy, as to how it's defined and that sort of thing. Now, in chemistry, free energy is an acceptable term. If you look in the index of any nice authoritative chemistry book, look back in the back of it, and you'll see free energy as a term that's is there, and it'll give you a page reference, and there'll be maybe a half dozen pages in regard to it. Now, in chemistry, you have 3 different types of situations. You have one where you're physically mixing things only and nothing changes. You're mixing a mixture of things, and they still remain what they are, except they're just sort of mixed together. Okay, the second thing, in some chemical reactions, you have an endothermic reaction, which means that they absorb heat, and you'll know that because it'll be cold whenever the action starts taking place. Now, the third one is an exothermic, and this is where we're getting into the free energy aspect of it. And the exothermic deal, the energy you put into it is a lot less than what comes out. And a good explanation of that would be an explosive device of some sort, an atomic bomb or whatever. The amount of energy that you put in there to cause that thing to explode is only a very finite amount of the energy that's going to be coming out. So if someone says that you can't get more energy out than you put in, you can tell them that how about explosives or atomic bombs, and there's a long list of things where this goes on. It's nonlinear, and it's greater than the input. Now, whenever you get to the electron, you're getting an overlap into physics. And the electron in your EMC square thing, the mass would be your electron, and the C squared thing would be your frequency, or the amount of times that the electrons are being flipped. And the MC square thing is wrong, because that's a linear type thing, and this is a one-dimensional linear type thing, and the electron thing is a three-dimensional thing, which most of your university professors and people that work in that type of thing use cubed instead of squared. So it's EMC cubed is the correct terminology, although most of the physics books use squared. And that has your inverse square law built into it and a whole slew of other things. So if you're at some distance from the source and you measure it and you know that distance and you know what your reading is, you can relate to what's there. For example, from a reading here, if there's a transformer in the back of the room running and I'm getting a reading on it here, well, I square the distance or cube it depending on which way you want to go, and the reading here times the reading I'm getting here, and that will tell you what the reading is there. Now, this concept is very useful in building Tesla coils or anything else which has a large amount of voltage which you don't want to actually stick your finger into. It's something that you have respect for that has a lot of electricity there. You don't really want to touch it, and you don't really want to stick your instruments into it while you're holding on to them sometimes. Now, they make special instruments that you can do that with, but you don't have to, because you can read the magnetic flux that's coming to you fairly easy, and you can relate that to the electrical flux, which is the flip side of the coin, and then you can convert that directly into the voltage of the object which you're measuring. And that relates to the little Gauss meter that I showed you. That, excuse me, the bookstore has some of these. And we were talking about it, and it ranges from 1.5 milligauss up to 30 milligauss. And that doesn't sound like a lot, but when you're some distance away and you get a reading, which is 3,000 volts equivalent, say out here, and you have to square that or cube it depending on which way you believe, depending on whether you're a college professor or somebody in research that knows that they're dealing with a three-dimensional thing. In that case, you have to cube it. Because, see, this radiation is going out in all directions. It's not just coming towards you. So if it was just coming towards you, it would be squared. That'd be linear, and in linear type things, the free energy or greater energy out than in can't happen, and that's probably why the textbooks don't go into the cubing of it. Because the moment you put that cubing thing in there, you're off into a free energy area. And as we were saying, the electrons in certain types of devices, when they're flipped in certain ways, you end up cascading the electrons. And when you do that, the electrons that you have, a certain small amount, will be incorporating all the electrons that are in the areas they cascade. So it's just like an avalanche. The term that's used in radio type books is avalanche effect. So if you've got an electron, say like the snow on the side of the mountain, and this little snowflake cuts loose and the whole side of the mountain comes down, so did you get more energy out than you put in? If the people want to tell you that you can't do that, they don't believe in avalanches. And so anyhow, what we end up with is a formula in the shorthand method, which all people that are supposedly scientific ascribe to. We have A is equal to ambient or background, because ambient is what you're working off of. And we'll go into that in a little bit, but the acceleration constant, cycles per second, and F, which we're going to let be free energy. It's delta G is the term which is used in chemistry and physics books for free energy. It's delta G equal, and then the formula, and then what you got here equal what you got here, and what's over here is greater than what's here, so therefore the free energy is what's here. And based on that, we were talking about ambient. There are ways to figure ambient, and almost everyone that's in the business of teaching physics or engineering or anything that's directly or indirectly related to electricity would tell you that the Earth's electrical field is very small or totally insignificant. Well, there are some things which are available publicly which disagree with that in great quantities, and I'll kind of give you a few of them. During the Cold War, the United States was searching for minerals that related to atomic energy and various sorts of things, strategic minerals, and one of the devices that's used to do this, there's an electrical signature difference in that help you identify certain minerals. But this is an offset from the petroleum industry from which I came, from which these maps were developed. You fly a magnetometer which measures the magnetic flux in gammas, say at 1,000 feet above the ground. And these things have been flown over every square inch of the Earth, including the oceans and everywhere else. And they read through the water or the surface structures. If there's anything in the area there that's interfering with the Earth's electrical field, you either get electricity spinning up. We were talking about the shield a while ago. The Earth's magnetic field, when it goes along, it's either flowing into the surface of the Earth or flowing out. And so you get a reading, a signature reading there as to the magnetic flux level, and that magnetic flux level at 1,000 feet in the air ranges greater than 1,900 gammas. And so if you're 1,000 feet away using the square law, that's 1 million times 1,900, or if you're using the cube law, you get quite another number. So anyhow, using the square law, we're getting off into the ambient background where you're sitting in many places is approximately 190 million volts. And that's stable everywhere. So if you take instruments and try to measure it, and if you measure from here to here, you're not going to see any difference. That's the bird standing on the high-powered line and not being aware that there's 250,000 volts between his feet. The electrical difference between the 2 points is not enough to be measurable. And all of the measuring instruments that are designed for electricity are from one point to another. So there's ways of getting around that. There's several ways of getting around it. There are the gamma thing that we're talking about, where you can take an indirect reading and you don't have to plug anything in. And then you get electrostatic voltmeters and a number of other things, and you can read directly something that can be converted into the actual true amount. Now, if we take that 190 million volts, and we were saying that the speed or cycles per second was feeding into it, well, we have to feed in the speed of the Earth going around the sun and the speed of our solar system passing through the galaxy, and the speed of the galaxy moving in which direction it's moving. So when you do all of this, you come out with hundreds of trillions of volts ambient background. And if that's meaningless, inconsequential Earth electricity or background, I would like for somebody to tell me otherwise. But there's plenty of evidence. Yes?
You're maybe an amateur radio.
I don't hear very well.
Well, you're maybe a radio amateur operator, and everybody turns on the radio can hear the ambient.
If everybody turned the radio on at the same time?
The ambient, of course, varies, but we can hear it at any time.
Well, there's something that relates to that, and whenever you have supposedly electricity moving from one spot to another, that is not completely true. When you excite electrons here, the magnetic wave which is transmitted causes something which is set at that same frequency at some distance to repeat and duplicate what was here. The electrons here did not go from point A to point B. A good example of that would be if you have this satellite out past Pluto and it's got a 9-volt battery in it, which they did have, and you're back here on Earth and you're getting all kinds of signals and readings from that planet, from that satellite, and it's out there hundreds of millions of miles away. You can rest assured that the same electrons that were out there are not the same ones that you're looking at here. Now the same thing is true at your house. The electrical power company causes an upset or disturbance of the electrons, which results in a certain potential at the electrical power company. Now at the lower cycles you have to use something solid to transmit this magnetic effect through. So at the lower cycles, below radio frequency, you have to have something that's connected between the two things. It's just like if you had like Beethoven, when he was composing all of his music, he was totally stone deaf, and what he did, he took a piece of hardwood and stuck it on the back of his ear here against the bone and leaned the other end onto the soundboard of the piano, and he was able to compose all of the interesting music that Beethoven that you see today. He was totally stone deaf. Now the reason he could do that is that the frequencies down below radioactivity are still part of the electromagnetic spectrum, and by disturbing one end of that stick there, the other end reacted the same way. But the electrons that were on one end of it were vibrating to match those on the other end. Now another way to look at it is, if you have a tuning fork of a certain frequency and you have hundreds of them in the room, and you hit this tuning fork and sit it down, all of those will be vibrating at the exact same sound level as the one that you have in your hand. Now another way to look at it is that in a piano, on the higher notes in the piano, they could not build the strings long enough to take care of the frequency situation. Now in the heavy end, on the heavier notes, the wires are larger and they have a winding around them which takes care of the frequency for them. But on the higher notes, they have to have 3 sets of wires, and the hammer hits the center one, and the 2 side wires vibrate at the same level and the same sound, same quality of sound as the one that was hit by the hammer. So there you have you have the original energy, and you have a couple of duplicates of it at the same level by hitting it at just one spot there on one string. So if anyone likes to tell you that you can't get something back that you didn't have before, additionally on the piano you have harmonics in frequencies. So you'll have all of these different harmonics in there. If something is tuned into those harmonics, you will get duplicates of your original energy source. Now this applies to sound level things. It applies especially to radio frequency devices. And this is one reason why we can build avalanche type devices like multifactors and your microwave, the cholesterol in your microwave oven and that sort of thing. Now if you have something you can read the magnetic field on, anything that's running, any machine, any transformer, any wire that's supposedly carrying electricity, a large part of that, equal to the amount that's going through, is being bled off into space. So anytime you get greater than 50% efficiency on something, you've actually really got 100%, because the amount of electricity that's coming through there is equal to the amount of magnetic flux that's being thrown away. So the total energy package there would be equal to both of those, or double the amount of electrical energy that you're getting out. So an interesting thought on that. For example, a motor that's running, a transformer that's running, a microwave oven that's running, and that sort of thing. If you build a coil system around it or anywhere in the local area there, and you tune that coil system to the frequency of the device that's emitting the magnetic flux that's being thrown away, it will not diminish the source at all. But the magnetic flux will be cutting the wires in the coil system that you have, a long wire or one that has, for convenience sake, been wound into a coil. A coil is actually an antenna that, due to the length of it, it would be impractical to keep it out in a straight form. So when you do this, you start gaining again, because when you wrap these layers of wire, they react with each other in capacitance and inductance way, such that each time it cascades from one wire to the next one, you've got a multiplication factor. And that's why on your Tesla coil, you can have, like say, 1,000 volts in and 400,000 volts out. Now this brings up another interesting question. First thing anyone will tell you, lots of potential but no amps. Well, I can assure you, if you put your foot in a bucket of water and you touch that Tesla coil, your problems are all solved. If anybody wants to try it, if they're ready to check out, that would be a good way to do it. So basically what potential is a certain level of electrical energy that's behind the dam. And depending on how much of it you want out at one time, or how much is required for whatever thing you're doing, you poke a hole in the dam depending on the amounts you want to come out. And that's your load. You put the load on there, and the load is a kind of resistance thing that starts interfering with the flow of the current, and at that point you've got amps. Before that, you had no amps. Yes, sir.
One question I'd like to maybe have cleared up, and you were kind of talking, I started visualizing it when you were talking about measuring your ambient. You talk about electrons flipping.
Flipping the electron?
Right. Now, that to me, in my mind, shows two-dimensional or two-sided.
Shows what?
Two sides or two-dimensional.
Yeah, well, you have the equal and opposite thing, which everybody would probably agree on, or Lorentz effect.
I guess what I'm trying to understand are the electrons, I mean, are they spherical in nature, or?
Okay, well, let's do this. Let's back up just a little bit. And in nuclear magnetic resonance, everything that exists, part of its being existing is the fact that it's resonant. That means that everything in your body, every part of your body, every part of everything that exists has a particular resonance. And this is getting into nuclear magnetic resonance. It doesn't have to be nuclear material to resonate. So anyhow, the particular atom that you're talking about, for practical purposes, things like metals and when you start flipping electrons, it's more convenient to use something which has high permeability and will conduct the magnetic wave that helps carry the electron process on.
Well, I think to help me understand the whole...
Did I get even close?
Well, is it more like an inside and an outside thing, and then...
Well, it's an abstract thing to begin with, because you don't see the electrons and you don't know that they're doing that, but you know that when you do certain things like magnetic, that you end up with electricity, and when you do induction, and whenever you do certain things electrically, you end up with a magnetic field. So it's reasonable to assume that something is flipping one way or the other. And since the electron is a source of electricity, it's safe to assume that that's what it is. Now, Thomson, back in 1911, at the time that he described an electron, nobody had ever seen one, and probably not until fairly recently has anyone seen one. And the microscopes and other things are such now that you can actually get down to that size. But the electron was a theoretical thing based on certain things that happen. Now, electricity, if it comes from electrons, it's a theoretical thing, but the results are, you're having to judge it by the results. For example, if something is painted orange, it's reasonable to assume that it's orange. You know, if you're getting certain actions, then it's reasonable to assume that something is there which is varying and is providing what you're getting. So
Okay, I guess what they talk. They're talking about directional flow.
okay, directional flow. Electrons never move very far.
Well, okay.
Okay.
What I'm trying to understand is this.
Okay.
Especially in relationship, you might say, to the whole infinite universe, or a very infinite, or a very, very far distance.
Okay.
Okay, now if you have the flipping of the electrons, it's kind of like, I'm wondering, you know, the two poles. What are your absolute, you might say, relative
Okay.
judgment points?
Okay, I understand what you're saying now. The speed of light is assumed to be the speed which electricity moves, but that's not the speed which magnetic waves move. There's considerable debate over it, and magnetic waves exceed the speed of light considerably, and if an electron is flipping here, all the electrons probably in our solar system know about it.
Okay, well, they talk about, now they're thinking about maybe the electrons are starting to spiral down the wire now?
Yes, well, they theoretically form a cloud around the rod or the wire or whatever you have, theoretically, and they spin in a certain direction. If you wind your coil in the wrong direction, you won't get any electricity out. If you wind it, you have to wind the coil in a certain direction that corresponds to the spin of the electrons for the electricity.
This is why I'm starting to, where I'm not understanding the flipping, because if you've actually got electrons, say, with two sides, you know, the one,
okay,
the magnetic flux,
okay,
and then it's going like this,
yes,
down the wire.
yeah, and there's an opposite.
There's a different side being shown all the time now.
Yeah.
This is why I'm trying to find out if this is the best way to describe this.
Okay, let me back up a little bit. We need to talk about magnets, and we're going to be looking at those in a little bit anyhow. But in a magnet, you have a neutral area that's, say, in the middle of a magnet. It doesn't necessarily have to be in the middle. You can set it to where it will be just anywhere that you want it, practically, or you can set it to where there's no neutral area and it's only monopolar. They have monopolar magnets are available where there's no north and south. There's only south or north, but not both of them. So anyhow, in this magnet, the reason why this neutral area is there is because on one side of that block wall, the spin is in one direction, and on the other side, the spin is in the opposite direction. So based on that, when you cause an electrical disturbance or a magnetic disturbance, the system that you're working against there is equivalent to one end of that magnet or both ends together at the same time. Whenever you give the pulse, well, it sends out a magnetic field that goes to wherever point B happens to be, and point B receives whatever equivalent was over here. Okay.
So to simplify your definition of flipping, stated another way, whenever you create or influence an electrical particle, such as an electron, you can influence it using an electrical field, or you can influence that electron using a magnetic field. However, when you use an electrical field, the flip opposite reaction is you will produce a magnetic field.
Yes.
The converse is when you influence an electron using a magnetic field,
yeah,
you will conversely, or flip side,
they will go to the opposite of whatever that. If it's a magnetic field, they'll go.
That's your definition of flip?
Yeah, well, the flipping is something which you won't find in any books. some of the more recent physics books have almost identical what I'm telling you, but I didn't get it from them. I figured this out on my own without their help, but it's very comforting to pick up a university textbook and see that they're kind of headed in the same direction that you are. It makes you feel like that maybe there's not as big a difference as you might think.
So since you're equating it, that is your definition of flipping then?
Yeah, it's just going from magnetic to electrical or electrical to magnetic, and whether it flips or spins or whatever, the results are the same, yes.
Doesn't left hand and right hand spin?
Right hand or left hand flip, well, there's a rule of how...
Doesn't of the electron.
Uh-huh.
Doesn't that explain flipping?
Uh-huh.
The electron spins left, produces one field. The electron spins right when it's influenced by another field.
Yeah.
Whether it be electrical or magnetic.
Well, there's a general rule of hand where you put your thumb in one direction and the spin is like so, and then the other side is just the reverse the other hand so that the spin, instead of being this way, the current is or the magnetic flux is in this direction.
So is electron spin
in both cases.
flipping?
Huh?
Is electron spin?
I can't.
Flipping.
My hearing is not all that good.
Is electron spin,
Uh-huh.
whether it be right or left, similar to what your meaning is when you say you're going to flip electron?
I will have to assume so, and we can visit after the meeting, and I can probably answer you better. Okay?
Don, I think that if you take a look at the book, The Energy Machine of Joseph Minman, he goes to tremendous effort to show that how the analogy of electron spin is like the precession of a gyroscope.
Yes, it is.
Okay,
It's a
that's very
gyroscope.
good analogy. Now, I'm not critiquing Joseph Minman one way or the other, but it's a source of information that you might want to check into.
Yeah, the electrons, when they're spinning, they have a tendency to line up with magnetic fields or current flow or a whole slew of other things. You see that in the magnets when your domains, in order to have a good magnet, all the domains have to be lined up in a certain way, and if those domains can be flipped also, depending if you put a large current.
He asked me a question, I told him to wait because you're talking.
Okay. Okay.
I have another comment.
Sure.
Okay, where can I buy a monopole magnet?
Monopole magnet.
Yeah.
I tell you, do you know Jerry Decker and Keeley Network on the internet?
I've heard of Keeley, I don't know.
Yeah, well, it's KeelyNet, and it's in Dallas at Richardson, Texas. And Jerry Decker is the, he's not the webmaster, but he's the power behind it. And Jerry Decker has some monopole magnets, and where he got them from, I'm not rightly sure. I have never seen one, and I know they exist, and they're very interesting to me, and there may be all kinds of valuable things that they can do, but at this point I have no experience personally, so I couldn't really answer you on that.
Last thing I'd like to ask you, are we going to get down to the nuts and bolts nitty-gritty on how to build a magnet generator?
Okay.
That's why I'm here.
How far along are we on this thing?
Time for a break.
An hour and 10 minutes.
After the break, well, we'll start off on that.
Okay.
And are we near the break now? Or?
Yeah, we're on it.
Okay, well, back there, we understand it's break time. So,